Good day, ladies and gentlemen. Today's video, we're going to be looking at your ESSRT page number 3. Page number 3 talks about portion of the electromagnetic spectrum. I want us to focus on that word spectrum for a minute, which simply means all the variation, everything in between two extremes, right? Like, for example, the rainbow is a spectrum. It's a spectrum of color, which means between one high energy color or dark color all the way to a low energy color or low frequency color, and then you have all other colors in between. So it's a spectrum of light. So that's what the word spectrum simply means. Then that word electromagnetic, what that means is when stars carry out their process of fusion, when they fuse lighter element hydrogen into heavier element helium, the byproduct that comes out of it is the energy being released, the light, the heat, which comes to us from the sun. Now, that light exists in both electromagnetic waves and exists in both electric wave and magnetic waves. So as a result, that word electromagnetic simply means both as electric and magnetic. So you see that in the uh, image in front of you, you see these light waves are behaving in two manners. So in this way, they possess a kind of energy that enables them to travel through space and travels through vacuum, which means they don't need any media for their propagation. What I mean by that is other forms of waves like sound wave, talking to you right now, is coming to you through the air, it's coming to you through gas. So a we need the gas to propagate the sound coming from my mouth to your ears. Many other waves need things to travel through. They can travel through solid, they can travel through gas, they can travel through liquid. However, electromagnetic waves do not require any of that because they have their own energy. So they can travel through vacuum, they can travel through emptiness, they can travel through space. So the heat and the light coming from the sun is not coming to us through any medium. All right, so it's an energetic wave by itself. So in order to make sense of that page number 3, I need us to understand some properties of wave. We're going to take two from here. The first one is wavelength. Wavelength simply means the length or the distance between one crest of a wave to the next crest, which means from the top of a wave to the next top. That makes one wavelength. All right, and then that wavelength will determine frequency. Frequency simply means how many waves is coming to you in 1 second. For example, if you take this diagram to the right and we draw a straight line in that manner, and then we say this is 1 second, then we can argue that for the red wave with a longer wavelength, within 1 second, we can only have two crests. We can only have two tops of the wave. All right. So which means the frequency here is two crests for every second. While on the blue waves, the one below, we can see that it's about 1, 2, 3, almost four waves, almost four crests within a period of 1 second. So this is has a higher frequency, which means within 1 second, you are getting many more waves coming with to you within a very short period of time. So the frequency is higher. Simply put, the shorter the wavelength, the higher the frequency. And then the longer the wavelength, the lower the frequency. So with that knowledge, let's bring that to the reference table page number 3. Below this, I have put the wavelength in there to give you a pictorial view of what we are looking at here. So first, let's start with the increasing wavelength, which is this arrow that you see here. What that simply means is that as you go to the right, the wavelength is increasing from one crest to another crest, so that the wavelength keeps getting longer and longer to the right. To the left is opposite. You see that the wavelengths keep getting shorter and shorter from one crest to another crest. We are way more packed together. So, because the wavelengths are shorter at this end and packed together at the left side, you see that the frequency, the energy is increasing to the left, while the wavelength is increasing to the right. So the electromagnetic spectrum that we are looking at is all the various forms in which light exists. Light exists in different forms. Light can exist as ultraviolet waves, can exist as X-ray, can exist as gamma rays, right? In various forms. Think about it. It's pretty much like having potatoes. We can have potato chips. We can have potato French fries. We can have waffles fry. We can have curly fries. We can have sweet potato. We can have chips. We can have steak potatoes. We can. All of these are just made from potatoes, right? We just give them different names based on how they were made and based on how they were processed. So it's the same thing here. Light exists in different forms, right? The only difference here is that the wavelength that the light exists in, that wavelength determines the frequency, and that gives the light a different name. But we don't get to see all of these forms of light that comes from the sun. We don't get to see ultraviolet rays with our naked eyes. We don't get to see infrared with our naked eyes. We don't get to see microwaves with our naked eyes. We don't get to see gamma rays and X-rays, all of that with our naked eyes. The only part that we see with our naked eyes is a very tiny portion, a very tiny portion. So amongst everything that the sun radiates to us, the one we get to see is just this very little. Technically speaking, we are blind to most of the things that the sun is emitting towards us, because the part that we see is so little in the spectrum, is so little in the spectrum that scientists have to expand it. Scientists have to expand it to break it down for us to understand. But it's a very tiny, slivery portion that we get to see with our naked eyes. So keep that in mind. And also notice that the part that is visible to us, the visible spectrum, is the part that carries all the colors that we are able to make sense of the world. So red, orange, yellow, green, blue, violet. All of that colors are gotten from a combination of these. So that makes the visible parts of the sun rays, or the electromagnetic spectrum that we get from the sun. Now, beyond violet, any other color that is beyond violet is the ultra, which means deeper, beyond violet, ultraviolet, right? And then beyond ultraviolet is, like I alluded to earlier on, is the X-ray. And then beyond X-ray, we have the gamma rays. So annotate that and put that in your notes as well. Then beyond the red, moving to the right side, anything deeper than red, you have the infrared, and then you have the microwaves, and ultimately you have radio waves. So simply put, the radio waves are much more stretched. The wavelength are stretched, so the frequency is very low. All right. Okay. So let's summarize everything nicely, and then we do some practice question here, and then we move forward. First off, understand the key here. The wavelengths are measured in nm, which means nanometer, and nanometer is a representation of 10 to the power of -9. So, which means on this extreme right, where you have wavelength of 10 to the power of 9. So 10 to the power of 9, when you take that and you convert that to nanometer, you see that it's going to cross out, and 0 is going to cross out 0. So you are left with 1 m, 1 meter. So similarly, that means 10 to the power of 6 would be 10 negative 3. 10 negative 3, and then 10 to the power of 3 here would be 10 negative 6. So I just want you to make that annotation there. So as you move on to this other end, you're going to have 10, say negative, yeah, this one here will be 10 negative 9. My bad. All right, cool. So put that at the back of your mind as we move on. Remember, these are in meters, all right? While the ones that are already written for you are in nanometers. Next is frequency. Frequency simply means how many waves you get in 1 second, and that is measured in hertz, right? It's measured in hertz. All right, so 10 to the power of 6, that's an equivalent of 1 million hertz, 1 million waves received in 1 second, because 10 to the power of 6 is an equivalent of 130, and then that's an equivalent of 1 million. And then 10 to the power of 8 is greater than 10 to the power of 6. 10 to the power of 10 is greater, so which means frequency is increasing once again to your left, while wavelength is increasing to your right. So how does all of this make sense here? What are we exactly saying here? um Ultraviolet rays, X-ray, gamma rays, which are on the left hand side, they have higher energy and higher frequency. This makes them to be very dangerous. That's why we don't get exposed to them. If you are exposed to ultraviolet rays for too long, you can have skin cancer, you can get sunburn. That's why we avoid it by all means. And the ozone layer protects us from these harmful form of light that comes to Earth from the sun. So the X-ray and the gamma rays and the UV rays, which is the ultraviolet rays, the ozone layer around the Earth protect us from those because they are dangerous. A little part of the UV rays slip by once in a while, and then some people get skin cancer or get sunburn as well. Now, the extreme and more energetic one, the X-ray, is the one we use to see through our flesh, to see bones. So those lights are so energetic, they can see through your flesh and go all the way to your bones. That's why when you're taking an X-ray, you need to put on a protection or a protective covering while you are taking an X-ray. And of course, you are not supposed to take more than several copies of X-ray within a year, because you're not supposed to be exposed to it too much. So all of those forms of light that comes from the sun are dangerous, and we don't want to be exposed to it. Conversely, on the right hand side, where the wavelengths are getting longer and the energy is decreasing, which is the infrared and the microwave and the radio waves, those forms of light are less dangerous and less energetic. So that applies to the visible light spectrum as well, which means red is much more calmer compared to ultraviolet, compared to violet or blue. They have more energy. So violet and blue has more energy compared to orange and red. All right, that is it. So we're gonna just go through some Regents practice question, and then we move forward. Question number one here says all forms of electromagnetic energy have transverse wave properties. Yeah, we did discuss that electromagnetic waves exist in forms of waves. So yeah, that could be our answer. Let's see. Have the same temperature? No, they don't have the same temperature. Um, Red or infrared have way higher temperature than the other ones. So they don't have the same temperatures. They don't have the same wavelengths, right? That's what makes them to be different. They have different wavelengths and therefore different frequency. Have their own half-life? No, not at all as well. So let's move beyond that. So question number one, the answer should be A. Question number two, which type of radiation has the shortest wavelength? Have the shortest wavelength? Rather, visible light, ultraviolet, and infrared. Shortest wavelength. So if it's shortest wavelength, we should be looking towards the right side, because that's where the short wavelengths are around this area. So rather, we don't have that there. Visible light rays is right here, so that's what we'll be looking at. Ultraviolet even have shorter wavelength. Infrared, on the other hand, have longer wavelength. So our answer here should be ultraviolet. All right. Question number three. In visible spectrum, which color has the longest wavelength? Isn't that an interesting question? Has the longest wavelength. Okay, so I'm gonna follow red here. Okay, so in terms of wavelength, red is right around 10 to the power of 10, 10 to the power of 3, and then violet is a little less than that, because remember, wavelength is decreasing this way, so which means ultraviolet will have shorter wavelength. So red definitely should have way longer wavelength, because red is more to the right. So our answer here would be red. Definitely not green. Red is 10, it's 7.0 times 10 to the power of 2. Compare that to green, is less, as you can see. 5.3 is less than 7.0. And so is violet is 4.0. So definitely our answer should be red. Question number 4. Which form of electromagnetic radiation has wavelength between -6 meters to negative to and 10 to the power of -7 meters? So we said earlier on this is 1 meter, and this is 10 to the power of -3, and this is 10 to the power of -6 meter, not nanometer, meter. So definitely between 10 to the power of -6 and below would be visible and ultraviolet. So which is between -6 and -7. Could it be gamma? Gamma is right around here. Gamma is already 10 to -9. So gamma is out, short wavelength is out. Visible? Yeah, that could be our answer. Infrared. Infrared, on the other hand, infrared falls between -6 and -3. So it does not fall within that range. So definitely our answer is visible light. Next question. What is the basic difference between ultraviolet, visible, and infrared radiation? The difference, they're all forms of light. They're all light. The difference is their wavelength and therefore their frequency. So yeah, definitely the answer stands right across for us. All right, that's a wrap, ladies and gentlemen, and see you in the next video.